Well, thanks for joining all, and sorry for the winter wardrobe. We've had a bit of a weather event in Texas, and it was a little cold in my house today, but we're thawing out, and we're excited to share a little bit with you and what we've learned printing large scale and thinking about filament fabrication, as well as printing with pellets and flakes. So we have our contract print ninja, Samantha Reeve, on the call, who does a lot of printing with FFF large scale, as well as Helen, who has been leading up our testing with Gigabot X, our pellet printer, and also looking at printing from flake. We have Lewis, who is our customer support ninja, who helps guide our community as they get the printers out in the field, and has been exposed to a lot of their needs and experiences in over 50 countries now, as well as Jarek, our senior engineer, who has been with us for a long time, and Charlotte, who some of you might recognize, our community ambassador, who supports our community engagement. So with that, I'll turn it over to Samantha and Helen and the crew to step us through printing big.
Hello, this is going to be a conversation about designing for 3D printing. Ignore the incorrect dates and also just my name at the bottom. This is going to be a joint venture between me and Samantha Reeve. We don't care about that. Anyway, so Samantha Reeve, can you tell us about the first thing that you need to consider when designing a part for 3D printing?
Yeah, the first thing is make sure that your part will actually fit in the printer. We make large printers here, but that doesn't mean that people don't send us stuff all the time that doesn't fit in our printers. Also, when you try to make it fit in the printer, you should also consider that it fits in a logical orientation. So if you make something really long and skinny, well, technically it might fit in a printer if you go diagonal from corner to corner, but that's a really illogical way to print a part. And so usually if your part is too big and really pushing the limitations of the volume of the printer, then you may not be able to print it in a logical way.
What are some of the potential things you can do if your part is too big for your printer?
You can break it up into multiple parts. Whenever you break a part up to print it in two separate pieces, you should always consider how it's going to be reassembled. So it could be that you put holes in the exact same spot on both sides that you're then going to put a peg into. Depending on how much you can do with the geometry, it could be that you add some flanges on the outside that you'll then screw those pieces together. But whatever it is, you need to consider how you're going to then reassemble it.
Those are great ideas, Samantha, and we'll put a link in the YouTube video as well, and then in the description, excuse me. There's a great video by Matter Hackers that some of the Troy University students had a chance to view that talks about how the different types of seams you can make too, and slicing your file so that you can print outside of your build volume.
What about considerations for rafts and skirts?
Yeah, that's another thing. So when you're trying to fit it within the build volume, you shouldn't go right up against whatever that number is. A lot of times you'll want something added to the bottom to help the part adhere to the bed. So for most high temperature materials, we use a raft. For a lot of materials that really don't want to stick to anything, like nylons or flexibles, we'll use a brim. And so a brim adds surface along the bottom, kind of like a suction cup, just increase that surface area where it touches the bed. A raft does that, but it also adds a little bit in Z. So I've run into the problem before where I put a part in the build volume and it fit in the build volume, but when I added a raft to that part, it didn't actually fit. And so I ended up having to print an extra thin cap piece to go on top of the part because it hit the limit of what the printer could print and hit that limit switch and stopped.
Samantha, could you talk a little bit about build volume considerations when you're using dual extrusion?
Yeah, so for most of our printers, when we use dual extrusion, how our dual extrusion works is the two nozzles are mounted together on the trolley. And for our left nozzle, we get the full build volume. But when we use both nozzles, we cut out some of that build volume. So the distance between the nozzles is roughly 55 millimeters. It can be plus or minus a millimeter or two in X and Y, but the bed is sized and the printer is made such that the left nozzle gets the full build volume and the right nozzle loses 55 to 60 millimeters worth. So if your part is pushing the limits of what it can do in X, then it's likely that either you'll have to rotate it 90 degrees so that then that's not a problem since it only limits in X, or you'll have to change the dimensions of your part so that you do get a full build volume.
Cool. Any lingering thoughts on build volume dimensions, or shall we go to the next one?
I did have a follow-up on what you're talking about the orientation, but is that going to be discussed in later slides?
I think so, yeah. We have a ton of slides on orientation.
Cool. Okay.
Yeah, so a lot of these considerations often act in conjunction with each other. And so it's important to keep all of them in mind. All right, resolution. Shall I talk about resolution, or are you itching to talk about it, Samantha?
Now you can go for it.
All right. So resolution refers to how detailed the surface and the different features of the part are, and it's related to the layer height and the layer width, and also the nozzle size that you were printing with. So if you want a higher resolution, you will use a nozzle size with a smaller orifice and smaller layer heights and smaller layer widths, and that will result in a smoother surface of the print. And then also you'll be able to achieve a lot more small features. Now, the downside of that though is that increases a lot of print time, right? Because if your layer heights are shorter, to print the same part, you need to print a lot more layers, and you are going to be extruding at a much slower rate. And then on the flip side, if you want really low resolution, then you will choose a nozzle size with a larger orifice, larger layer heights, and larger layer widths, and you'll extrude a lot more at a faster rate. So it'll allow you to print more with more material faster, but you may run into problems where that resolution is too low to be able to do certain features. And also at larger layer heights, the layers themselves become a lot more visible, so you'll have a rougher surface texture. So it's really kind of like a balance, right? And the idea is you want to design parts to require the lowest resolution possible, because that means that you will minimize the print time it would take to actually print that part and the associated cost.
I guess with that being said, do you mind just quickly going over what's being shown in that picture?
Oh, sure. So this is the same model sliced at different resolutions using our standard profiles. So the one on the left is with a 0.4 millimeter nozzle, and that is a 0.3175 millimeter layer height. And then we go on to the 8 millimeter nozzle, then 1.75 millimeter, and then 2.85 millimeter nozzles. So you can kind of see in the slice how it becomes a lot more visible, the different layers. And then on the rightmost one, we're actually having problems even printing the model because the geometry in the model is smaller than the print lines. So that one on the right is not going to be a good print.
So with Gigabot specific printers, like what size feature actually shows up well? And does it depend on the nozzle size that you're using?
Wait, can you rephrase that?
Sure. I mean, so if you have a small feature on your part, is it like at what size do you will you know that it will actually show up in the print or disappear because it's too small?
Oh, I see. So the width of an extrusion is about 1.2 times the size of your nozzle. So if you have any geometry that's smaller than that, then you're not going to be able to print it in the X and Y direction. In the Z direction, that's going to be limited by layer height. But there's also other considerations that can happen, such as, you know, heat buildup if your layer times are very short. Yeah, and I think the fail-safe way in practice to do it is, you know, have a general idea of what resolution you want, but then you can always double check it when you slice it, because there's a preview in the slicer that shows, you know, how the slicer is actually computing how to print the layer lines in order to achieve the model geometry. And then that's where you can catch a lot of errors that you might not have been able to catch in designing.
Thanks.
Yeah, I also want to say that your smallest feature can depend on if it's a standalone feature or if it's something that's incorporated. So like with this model here, if you can tell, it's got some lettering on it. And so with those lettering as indents, the printer can do that okay because it's part of a larger model. If you tried to print all of that as an extra part, let's say you wanted to do this in one color and the lettering in another color, all of those features would be so small that it really wouldn't print well, but it can do that as a cutout because it's part of the larger model.
And then there's also this kind of subjective effects too, right? Because in this yellow one right here, the model is slicing where the lettering is, but it's not actually that readable or legible. So there's additional considerations to consider besides just, can it print this feature? It's also like, to what resolution can it print that feature such that that feature meets your requirements? All right, shall we move to the next slide? Okay, Samantha, you've got this.
Okay. All right. So orientation makes a difference on the strength of your part. So the way FDM printers work, or at least all the ones we use do, is it goes through and it traces out and prints one layer at a time. And so the strength within that layer is much stronger than the strength between each layer. Because you have liquid plastic that's connecting to liquid plastic on most aspects of within one layer. But when you're putting the next layer on top, the layer behind it has already cooled. And so, especially if there's an enclosure, it may not have cooled all the way cold, but it's still significantly cooler than the plastic that's liquid that's coming out of the nozzle. So the bond between the plastic there isn't nearly as strong as the bond to the plastic to its neighbor that is roughly the same temperature as itself. And because of that, that affects the strength of your parts. So parts along the layer lines are really weak in tension. They're fine in compression because you're just squishing the part on top of itself. But any scenario where it's in tension, so even if you've got a compression that then creates a moment that section is in tension, that's going to be a problem. As long as that's just going to be the weakest aspect of your part. You can still print parts that are then pulled along those lines. You just need to consider the strength of your part. So how much material and surface area is there? what's the strength of the material, all these other things. It needs to be a lot stronger to take loads along that axis. So for example, on the left, you can see the picture where a part has actually split. It was the chamber wasn't hot enough while it was printing. And so there were a lot of internal stresses. The part wanted to shrink, but part of it wasn't ready to shrink yet. And so when it had all those internal stresses, it broke at those layer lines because that's the weakest section of the part. And then the middle picture, when you're printing circles, circles print a whole lot better in that right orientation where you've got the circle that goes straight up. So your part is going to look a whole lot cleaner if you print like that. But if you need that to have more strength, you may need to lay it down on the bed like the one on the left. For the shelf on the right, there's different ways you could print that. So one way is to print it flat on the bed. That's probably going to be your best bet. The problem there is you have to really watch for warping, especially if you already have some metal brackets that's fitting into. You could put that up on its side long ways, because a board like that, you're worried about the stress in the middle. So if you sat it up such the longer thin edge was on the bed, that could also work, but you really don't want to put the smallest area edge on the bed. That's going to give you the weakest possible scenario, and that board is much more likely to break.
Yeah, so thinking about the shelf as an example, it's really important to think about not just the overall strength of your part, but if there are specific forces that you intend that the part to be subject to, and from which direction are they going to come from, because that can impact the best print orientation in order to give your part the strength it needs.
I think in this example, specifically, it's also important to note that not every single piece of your part needs to be 3D printed. So if you're making a custom shelf, for example, you could design the brackets to hold the shelf that would fit in the custom spot, but you could get an off-the-shelf solution or reuse a piece of existing shelving that is, a very basic shape that would be potentially more successful than a 3D printed version of the same shape.
Speaking of that, maybe the best solution is to divide whatever the part is into multiple parts, and then those individual parts can then be printed in the orientation that makes the most sense for their specific needs. So like this shelf, it looks like there's this board and then there are also these brackets, right? So maybe it makes sense to print those parts separately and then orient them such that the orientation serves the strength needed for those specific parts. Okay, well, that was one aspect of how to decide the best orientation for your part, but there are a lot of other ones too. So next, support. Samantha, tell us about how to orient with support in mind.
So yeah, so there's different things that you want support to do. So sometimes you want support to just support the bottom layers. So unfortunately, we can't turn gravity off. We have to stick with gravity, and we need something under. So if you're printing a T, then the edge of that T is going to need support, because when it goes to print out there, it needs something to put that plastic on top of. And so when most people think of support, they think of just those sections that are going to need support. So generally, when you pull a part in and you're going to print it, or you're going to design it, you want to think of which side is going to go on the bed. Which side do I want to put chamfers or different angles such that it doesn't need support? The printer can print an overhang to an extent that won't need to be supported, but flat overhangs will always need some sort of support. Another aspect of support, like you can see in these pictures, is also for stability. As your part goes, it needs to not fall over. If your part falls over, your print's done. If at any point your part comes off the bed, there's nothing you can do to save it. Most any other scenario, you can save it with lots of work. But if the part comes off the bed, you can never save it. So the head of the person on the left, supported surfaces also usually aren't as clean as other surfaces. So generally your cleanest surface is going to be what you can see while it's printing. So it's all the XY that is, so not in XY, but either XZ or YZ, that side of the part when it's stuck to the bed, that's going to be your cleanest surface because your layer heights are generally smaller than your nozzle size. Along with that, the next thing is going to be anything that's facing up. So next best surface is anything that is not supported. So in this face, I have the face facing up so that the face doesn't have any support at all. Because if you add support onto that, that interfacing of where the support is, and also those overhangs, that gray zone of like, it doesn't really need support, but it's still an overhang. Those are also not as clean of a surface. So when you're orienting your part, as well as designing your part, you want to preferably design it to need as little support as possible, which saves print material and time, and so therefore cost. But it also saves post-processing time because once the part is printed, you will then need to remove that support, as well as the quality of your part. You're going to get the best quality part for surfaces that aren't supported.
And when you say surfaces that aren't supported, it's surfaces that don't need support, because if surfaces, the overhang angle is over than 55 degrees, I think is our standard, then it will need support. So if you try to print it without support, it's probably going to be a hot mess, literally. So in those situations, yeah, use support when you need it, but try to design or orient such that you can minimize the amount of support that you actually need. Oh, and then there's one more note here. If you're having trouble figuring out how much support you need or how it affects the print time, you can always use a slicer program and pull your model into it. We use Simplify 3D, and it has an estimate for the amount of material and time that a print will take. So you can do that and slice it in a certain orientation and see those estimate numbers, and then change the orientation, reslice it, and see if it uses more or less support, because sometimes it's a little difficult to tell what orientation is best, especially for abstract pieces like the picture on the right here. All right, any other questions or thoughts about support?
I think there's a lot more support imagery to go, so let's keep going.
All right. Well, you thought we were done with orientation. We're not. There is another thing about orientation. I can do this one. So one thing to consider when orienting is it's best to orient the part such that the side of it that's facing the bed has a flat bottom. And that will just ensure a good bed adhesion so your part doesn't fall over. But also if you have a part that's like the one above here on the top, where it's almost flat but not quite, that means that you basically have to have support under that entire area of the part. And it just adds a ton of print time and support removal time that, you know, if you were to redesign this, maybe it's simpler just to make that side that is almost flat actually flat, so that you don't have any support at all needed under there. Ooh, this one's a fun one. Samantha, you want to talk about it?
Sure. Just because you look at a part and it says it'll print and it doesn't need support, doesn't mean it will actually print and not need support. So let's say you added enough support so it didn't fall over. Well, if it's on the border of falling over, you might get vibrations. So really tall and skinny parts, or just other really skinny parts, whether it's just like a pole straight up or a flat plane, those tend to not do well. There is a little bit of friction as the nozzle goes across the top of the part to add more plastic, and that little bit of friction can cause vibrations. So you can see this print is a mannequin arm, and it didn't print well. Nominally, it did stay stuck to the bed. The support could be removed, but towards the top, it was vibrating so much. You can also see towards the very top, it gets a little better. That's because we walked by and slowed the print down, not that the print recovered. So as you go, you can either slice to slow it down, or you can add bracing to avoid vibration. But another thing with this part is to try to lay it down. So it's not so long that it couldn't go closer to the bed. It's just a balance of this part has curved surfaces everywhere. So there's no good flat surface like Helen was talking about to put on the bed. Also, every surface that is supported is a poor quality surface. So sticking this arm straight up gives you theoretically the best outer surface because it's along that z-axis. It gives you the cleanest print, but only if it can actually print that.
Mm-hmm. And to clarify, the vibration is happening in the print itself, right? The printer frame, the extruder, the bed, those are all held pretty rigidly in place, and their placement is very precise. So it's the print itself that is vibrating as it gets taller.
Yes, and the print stayed completely stuck to the bed. So it was rigidly attached to the bed.
Mm-hmm. I guess the other interesting thing about this arm is that we talked earlier about how if you have parts that are oriented like in the Z like this, that means that it's going to be weakest. So like if you try to karate chop across that arm at the elbow, because of this orientation, that's going to make it weakest there. But you know, we've talked about all these different factors that go into how you orient a part, and sometimes some will be at odds with each other, right? So this orientation may be great for reducing support and improving surface quality, but then it's bad in terms of vibration and strain. So it's really like balancing all those different factors when it comes to orientation. Oh, there's another orientation one. Okay, I can talk about this one because this chair makes my blood boil. So there's one aspect of orientation, which is understanding the center of gravity of your entire part and making sure that that is not going to cause a moment while the part is printing such that the part tips over. So this chair shown here, it does have, it's set at an angle such that it technically doesn't need support to print that angle, but because of where the mass is on this particular part, as that prints from the bottom of the bed up, the center of gravity is going to slowly move further away from where the part is stuck to the bed, that it will create a moment, and then that part will fall over. And there isn't really like a precise way to calculate this very well. You just kind of have to like look at your part and kind of guesstimate where the center of gravity is. So yeah, your slicer will let you slice this just fine. And it's really just like, you gotta watch out for this.
So what would you do with this part specifically to make sure that it was a successful print if it had to be printed in this orientation?
If it had to be printed in this orientation, then we could add support.
Mm-hmm.
But I would also question, like, what can we do to make it so it doesn't have to print in this orientation. So that was what we eventually did with this part, because the side that's kind of facing away from the screenshot wasn't quite flat. So that's why it couldn't be laid on the bed, because then there would be too much support and the surface would be really poor. So this part was just redesigned to make that face completely flat so that it can actually be printed flat on the bed.
Thanks.
Most CAD programs will also give you a center of mass, although that is going to be off because that assumes that your part is solid all the way through, where usually with 3D printing, your outer shell is thicker and your infill is lighter.
Yeah, and it's really about the center of mass being over the part that is attached to the bed, right? Okay, that concludes the orientation section. And here's the support. I think we kind of already talked about this a lot at length in the orientation section. I don't know if there's anything more you want to add to that, Samantha? Nope. Okay.
This Samantha would add that I think it's really important to foot stomp though, that as you can see with large prints like that, that's a lot of material, which not only takes time, but can cost money. So if you're on a budget, it's really important to think about ways to minimize support, or if you're under a time crunch. And then, we'll highlight it as we go through this, but not every print, as you've seen, works the first time. So you also want to calculate that time for failure and the material that might be consumed.
Mm-hmm. All righty.
So I'll talk about this one. So when you're putting in support, you're putting it in so that the part will print. But the other thing is you want your part without the support in the end. So you have to be able to remove it. So sometimes that could be an internal cavity that's really hard to get to. Like, for example, if you want to print a snail shell, then you're not going to be able to get to the inside, just due to the geometry. And sometimes you may be able to get to everywhere, but whenever support is stuck between sections of a part, when you're removing support, the easiest way to remove it is to pull on it or something in a way so that it can move somewhere. If there's nowhere for the support to go, if it can't move anywhere, then it's a lot harder to get out. So for example, these little screw holes on the part in the middle, those can just be pulled out to the sides and there's a path for the support to get out. If you've got a really thin channel, like those holes, that it's too close together, and it's just dense support, because there's the lower density support and higher density support. If it's just higher density support, there's nowhere for that support to remove, so it's really hard to get it out. And so there's parts where it's hard to get it out, and then there's just parts that it's really hard to get to. So like this part in the middle, that hole that you can see in the front connects up to the hole at the top, and it can be hard to get tools in there to actually get that support out. And most parts won't work as intended if you don't get all of the support out. Occasionally they will, but that's not something you want to count on. If it could work with support there in the first place, then you should just design bracing there so you don't print support and try to remove it. Another option with this is dissolvable support. You can use different material support, kind of like the picture on the left, which means the support can be closer to the part, and because the materials are chemically different, they don't bond as well, and it makes the support easier to remove. There are a lot of other complications that come up with that. So using a different material support adds 1 minute per layer as you cool down and heat up. So for a really long part, I've had that dual extrusion time that's added be over a day long for like a week or two long print. And so that time can really add up. Another thing is the complexity. You've got more moving pieces. You've got more things that can go wrong. If your part grinds through and stops printing on a single material print and it stays hot, it can almost always be recovered. If one side grinds through on a dual extrusion print, it's not necessarily recoverable. So adding a second material or just switching to a really fancy material like dissolvable support can add a lot of time as well as money, since the dissolvable support is a lot more expensive than most other support materials.
So is cost the only reason why you should not use a dissolvable support for all your support needs?
I hate using it. It's hard. Everything goes wrong.
Explain.
Yeah. So PVA, which is the most common dissolvable support, dissolves in water. So the good thing about that is water is a very accessible chemical and is not hazardous to use. There are support materials that dissolve in chemicals, and then you have to worry about whatever chemical disposal for those chemicals. The bad side of PVA is it dissolves in water, and there's water in the air, and it degrades with the humidity. And so we're in Houston, which has a very high humidity, and so we need to constantly keep that material dry. And so we have to dry the material, keep it in a dry container so that it feeds from a special container while it prints. It's also tends to be very much more picky with the extrusion temperature. It has a narrower range than most other plastics. Most plastics, when you're too cold, it just won't extrude right. But when you're borderline too cold, you get more of a matte finish. When you're a little hot, you'll get a very glossy finish. And if you get really too hot, then it can burn the material. PVA has a very narrow window of will extrude to will burn. So with many PVAs, that could be a temperature range of like 10 to 15 degrees. Whereas for most other materials, that's going to be at least like 20 to 30 degrees. So it's a much smaller range. Also, because that range is so small, when you're printing dual extrusion, it goes back and forth. There's time at which the nozzle spins hot as it's cooling down to let the other material print. And during that time, when the PVA sits at print temperature, while it's cooling down, it can start to crystallize in the nozzle, which then clogs the nozzle and your print fails.